Good afternoon, everyone. I'm Sriram. I'm planetary radar scientist. Let's move to the other end of the spectrum, which is the radar. So radar is a powerful tool to understand planetary geology because of its ability to penetrate some materials and reveal the subsurface structure. And it's the only instrument which can actually look into the PSRs. The background image here is a ground-based radar image of crater called Shoemaker near the lunar South Pole. So this was taken in somewhere in the 90s or early 2000s. So this is the outline of my talk. I will just start with a little bit of jargon because you'll be hearing all these terms for the next 20 minutes. And then how do we actually detect water ice? Because radar does not detect molecular water. This is important to note. It can only detect the presence of water in the form of ice through its scattering properties. And then the central theme of the talk, which is the lunar poles. And then an important piece of puzzle is the distinction between the radar properties of the poles of Mercury and Moon, because both are airless bodies, they have similar sizes. Of course, Mercury has a weird orbit, it has a 3:2 spin resonance, but still the polar environment is the same, but still we observe very distinct radar properties. And where are we now as per our current understanding, and in what direction are we going? So as I mentioned earlier, it's a very useful remote sensing technique because radar is sensitive to the structure, that means the geometry of the target surface, composition through the dielectric constant, and then electrical properties also included, and then the roughness, because radar typically operates in centimeter wavelengths. That is the range we are talking about here. So typical planetary regoliths encounter surfaces which have the size distribution from centimeters to decimeters through meters. So radar is sensitive in that range. So in radar, we measure all the aspects of the EM waves, starting from frequency or wavelength, and then polarization, which is a very important parameter when we talk about the ice, and then as well as amplitude, we call it as intensity. So when these are fixed, we are concerned with the incidence angle measurement because radar operates from a side-looking geometry, and the incidence angle it makes with the surface normal, it's a very important property. So radar gives different kinds of responses based on the target surface is measuring, if it is smooth or moderately rough and rough. So you can see that rough surface is practically independent on the incidence angle compared to a very smooth surface, where when you observe it at near nadir angles, it looks like a mirror surface, which gives a high intensity of backscatter. So this is the term which you might have heard or seen in the news, that radar has detected water ice somewhere on Mercury or Martian poles or lunar poles. So this is the important parameter. So what happens is you transmit a circularly polarized radar signal from Earth. So all the heritage we have is from the ground-based radars. So radars transmit circular polarized because it's a convenient way to obliterate the effect of Faraday rotation, Faraday effect. So you transmit in one sense and then record the signal in both the same sense and opposite sense. So for example, if you transmit in left circular, you receive in both left and right circular. So these are kind of orthogonal polarizations, and the ratio of this is called the circular polarization ratio. It's a very sensitive indicator of near surface complexity, that is near surface roughness, and the same parameter is used to detect the presence of ice. So you can see here, all these OC signals, they are enhanced by mirror-like reflections from the surface. Whereas if you have surface undulations or these kind of wavelength scale scatterers, either on the surface or within the depth of the penetration of radar, those kind of interactions will enhance the same sense circular. So when looked at by radar, so you can make a first cut reference of whether the surface is smooth or transitioning from smooth to very rough. So these kind of CPR ranges are observed. When it is moderately rough, you will have both these polarizations almost similar. But when you have very high roughness, so the SC component will be enhanced compared to the OC component, that is opposite circular, and you will get a high CPR value. So this ability of this radar to investigate the subsurface, it gives us a unique perspective with which you can explore different geological properties, including the presence of volatiles. So what are the different kinds of radars we have for lunar exploration? This is the Arecibo radar in Puerto Rico, which was operational till 2021. Unfortunately, it fell down. This is the largest ground-based asset we had. It was operating since the 60s. So this operates at S and P bands, that is the 13 centimeter and P is the 70 centimeter. So they transmit circular polarization. That's why we have a heritage of these terms. And then in 2008 and followed by 9, there are these Chandrayaan-1 and LRO missions. They have both these radars. Collectively, both are called mini RF radars, but in Chandrayaan-1 terminology, it's mini-SAR, and in the LRO, it's called mini RF. It has a single frequency, that is S-band, while the mini RF has two frequencies, that is S and X. So X is the higher frequency one. It's around 3 centimeter. So this is our current DFSAR, dual frequencies are on board the Chandrayaan-2 orbiter. So there is a small distinction between all these in terms of their transmitting and receiving capabilities. So these ground-based as well as these mini RF radars, so they transmit in circular and receive. So Arecibo receives in circular, whereas both these two receive in the linear sense. So kind of compact polarimetry. Some people term it as cheap polarimetry because you are transmitting in one sense and receiving in two senses. Whereas the DFSAR, it has the fully polarimetric capability. It is the first such instrument sent outside of the Earth for a planetary mission. So this is referred to as the gold standard in radar polarimetric sense. So even though all these have distinction, the important thing to note is that all these instruments can generate the CPR parameter, which I have described earlier. So how does water ice gets detected from radar? The theory behind this is the coherent backscatter opposition effect. It's in quantum physics, its equivalent is weak localization theory or time reversal symmetry. I don't want to go into the specifics, but what happens is when these radar signals enters into a weakly absorbing medium, such as an IC matrix, and then interacts with low refractive index material, such as voids or inclusions, they get forward scattered, which preserves the original sense of polarization. And then they interfere constructively and then goes back in the backscatter direction. So you kind of get very high intensity and it maintains the polarization sense. So what you observe is very high backscatter as well as the CPR parameter is very high. So in theoretical limits, the CPR goes up to 2. This was demonstrated in several lab-based experiments. So this was done, for example, on a gold surface sometime in the 70s. You can see the sharp peak. This is the opposition surge when you observe at a detector angle of 0. So the important thing to note is this CBOE is most effective when you have closely spaced, ordered structure of these inclusions, which are wavelength sized and embedded in a low lossy medium, such as water ice, because ice is what we are interested in. In terms of radar response, you can see that the rough surface generates typically equal OC and SC responses, whereas these kind of IC matrix generates a very high SC compared to the OC, which gives rise to CPRs above 1. So this is kind of indicator that radar is sensing kind of water ice matrix there. However, this is the thorn in the flesh, because high, extremely blocky surfaces also, gives rise to these kind of signals. We have examples on all planets. So this is a good terrestrial example. This is ST flow a lava flow in Arizona. This is a very blocky flow, basaltic andesitic lava flow. So these lava flow is associated with blocks of centimeters to meters, such kind of wavelength scale blocks. So when radar encounters these kind of surfaces, again the CPR goes up. So the important distinction we need to make in the analysis is whether we are observing an icy matrix or a very high rough surface. And another example from the lunar surface itself, this is a Tycho crater, which you can see from the naked eye. It has this ejecta blanket, which has very high CPR values because of these kind of blocky materials there. And two other examples from craters in the equatorial region, where you have these kind of impact melts associated with the craters, which also gives rise to these kind of enhancements. So ice is not only detected, talked about in the lunar polar context itself, because there are so many icy surfaces in our solar system. The best example from radar observations is the Galilean satellites, Europa, Ganymede, and Callisto. These are the two landmark papers done in the 70s and then in the 90s, because you need to wait for the favorable viewing geometry to observe these distant objects. So you can see in this, I want to draw your attention to this plot, that you can see how these three satellites have very high albedo, as well as their CPR is way above 1. And when you compare this with other features, so the Mars and Mercury lie somewhere here, and the average lunar surface is up here, whereas most targets in the solar surface, solar system fall in this line. So the takeaway is that for icy Galilean satellites, there is no evidence of specular reflection, and all what we observe from wavelengths starting from 3.5 up to 70 centimeter are mostly from multiple scattering. So the JUICE mission, which you might have seen, is going to find exactly this property, that what is causing these kind of high anomalous CPR values. The ocean worlds, we know that they are ocean worlds, but at what depths they are, what kind of ice is present in that. So they have a RIME radar on the JUICE mission. So this is the background for the water ice on the moon. So we started with the theoretical predictions in the 60s. There are several papers in the 60s. This is one of the seminal works by Watson. So all these works talks about the sources, whether they are exogenic or endogenic, and how once the source is identified, how they are transported to the polar regions, and after the transport, how they are ultimately stored for billions of years. So all these three are important if you want to detect the presence. So we started from theories, and then there are experiments, there are space missions, and after LRO, we have several wavelength observations like temperature, reflectance properties, and then neutron measurements, and then you have an in situ observation from the L-cross. So I just listed several different techniques that sense the presence of water, but you can see that radar only detects macroscopic blocks, which are several wavelengths thick. Okay, so let's start with the Clementine, because this is the first mission which talked about the presence of water ice at the lunar poles. So Clementine was a US mission in the 94. It transmitted from the high gain antenna. This is a bistatic experiment. That means your transmitter is on top of this spacecraft, whereas the receiver is at DSN of JPL. So they transmitted from the orbit and then observed a small part of this pole, which was collected at the DSN. Of course, the bistatic angle is 0, which effectively makes it monostatic. So what they observed is these elevated CPRs near the Shackleton crater. So this kind of first suggested that this could be the presence of water ice, which have been predicted by theoretical models. However, later, using the same data, some other colleagues indicated that there are ambiguities to this interpretation, and they questioned this validity of claims of presence of ice. So cut back to the early 2000s, because the Arecibo antenna was upgraded with new transmitting capabilities. So the South Pole was observed at both long wavelength, that is the 70 centimeter, as well as high resolution S-band data, that is 13 centimeter. And both of these studies indicated that there is no evidence for such high CPRs associated with any craters. And whatever high CPR we observe, it's not because of water ice, but they are associated with kind of impact melts that were generated in large impacts. So you have craters ranging from small craters to basins on the moon. And when this crater process happens, there is a lot of melt generated, and that get transported to these regions. And as well, the melt as well as the ejecta associated with those craters. So during the time, there was news all over that the story of water ice on the moon is done and dusted. We don't need to go back to the poles again. But again, this changed after Chandrayaan-1 and LRO. So a new class of craters have been identified at both the poles. So all these green ones are called CPR anomalous because only the CPR, high CPR was observed inside the crater, but not outside. And most of them correlated with the PSRs. So the argument was geologically, this is not possible that you observe high CPR only in the inside, but not on the outside. So with the first order and second order statistics of CPR compared to the surroundings, Spudis published this using both MiniSAR and MiniRF, that these elevated CPRs, they are correlated with other measurements such as the epithermal neutron flux from the lunar prospector. And they argued heavily that these are all consistent with the presence of ice. But after that, there are series of papers from 2013 onwards and till 21 or 22, which say that so what Spudis observed was not because of ice, but the radar data was not corrected for incidence angle geometry, because radar observes from a side-looking geometry, and the data needs to be corrected by taking the local topography into account, which was not done before. And these two studies indicated that there is no difference in the CPR values between polar, potentially icy, as well as non-polar, non-icy craters. So we did some kind of numerical modeling study, in which we took different particle sizes, particle shapes, and then propagated the polarization properties. And our major observation was that ice particles are totally indistinguishable from the silicate-rich particles, unless we can be very sure that ice plays a major role in the shape of the particles. This is a very important piece of puzzle again, because there was an Alcross experiment in 2009 where they bombarded the spent rocket booster into a region near the South Pole, the Cabeus crater, and using a shepherding spacecraft followed by that, they recorded the plume after the formed by that impact. So they recorded several components such as water, ice, vapor, as well as several other hydrocarbons. But when it was observed with these mini-RF radars, it was found that there is no such presence of high CPR in that Cabeus region. So this red dot is the approximate location of the impactor. It was observed in both Chandrayaan-1 and LRO at both at S-band. And you can see that the Cabeus CPR is in fact very less compared to the average polar region. So this again says that whatever the ice is detected, it's not within the detection limits of the radar. We also did similar study with L-band, because DFSAR is equipped with a longer wavelength radar. And both these results indicated that these results are not consistent with the presence of thick ice, but we don't rule out the presence of dirty ice. That means ice typically mixed with regolith. So another important aspect is the need for non-zero phase angle. So this is a landmark paper in the early 90s. What they did in the lab-based setup was they took water-ice analogs like polystyrene spheres on top of water, and they recorded this function, these polarization ratios as a function of phase angles. So in optical terms, you say it phase angle. In radar terms, you say it bistatic angle. That means the angle between your transmitter and the receiver. So the idea is if you observe your backscatter as a function of this phase angle, you can see this opposition surge when you reach the backscattering angle, that is 0. So this is the total intensity, and this is the circular polarization ratio curve, and this is the linear polarization ratio curve. And for comparison, they showed it with the surface of a silicate glass, analogous to the background regolith of the moon. And this result paved way for doing this kind of experiment with mini RF onboard LRO satellite. So the theory, this is a theory. When you have an ice matrix, it gives an opposition surge, but when you have rocks, it doesn't give this kind of gradual, it goes like this gradual curve with respect to the bistatic angle, but it does not give this sharp peak, what we observe with the icy materials. This is a bistatic image of Cabeus crater. So this is an important plot here. You can see that this is the surge observed with the Cabeus floor, which they predict to be the presence of ice. But when it is seen from monostatic observations, both from the Earth-based Arecibo as well as orbital-based radars, such kind of surge is not observed. So even though they observe that this surge could be due to the presence of ice, but they are not consistent with the monostatic observations that was done with ground-based radars as well as the orbital-based radars. This brings to the last part of my presentation. This is a curious tale of two poles, Mercury and Moon. As I have mentioned before, both have same polar environments because they are very cold, less than 120 K, and capable of providing these traps for volatiles. But if you see the response, when you plot this SC versus OC, the Mercury regolith is clearly separated from the background is clearly separated from the icy deposits, whereas this is not observed for the Moon here. So this plot shows how the Mercury poles have a huge range of this SC albedo when compared to other features such as these Ganymede, Martian polar caps, Callisto, and you can see the Mercury average is up here, whereas the poles have this huge range of variability in terms of this circular polarization ratio as well as the SC enhancement. So one of the important questions now is why, even though if they have the similar properties, why the radar properties of poles of Moon and Mercury are quite different. So where are we now? We definitely know that the ice, if it is present, it should be in the form of dirty ice that is mixed with regolith, or it should be at a depth which is currently not sensed by the radar as of now. So in case of Mercury, another interesting observation was that there are some regions which have CPR less than 1, but still contain ice. So on the Moon, probably this could also be occurring. So we need to concentrate on the regions where CPR parameter is less than 1 and use other different techniques in order to make sure that what we are observing on the Moon is probably similar to what we observe on Mercury or not. Bistatic observations, only Cabeus has shown a response, but several other features have been observed using the bistatic radar, but only Cabeus showed a response and we don't know why. So this is the current understanding. So these two scenarios will give you a response if there is ice. That means you should have this icy matrix at least hundreds times of wavelength. That is, it should be meters thick, but it should be covered with a regolith layer of very few centimeters so that the radar can detect the ice. And then in other case, These are like IC patches inside a radar pixel. So these IC patches should be at least 1/10 to 50% of a radar pixel in order to get a detection. Going way forward, we definitely know that CPR is not the unique indicator of water ice based on all the observations we have. This model shows that when you have, this is an example model where the surface layer is a mixture of silicate grains, ice, and then 50% vacuum, what you typically encounter in the lunar poles. So this scenario shows with no rocks, and this scenario shows with large buried rocks with different shape parameters. The C by A is showing you whether the rocks are oblate or prolate or they're just round. So you can see that there is a very little variation in the CPR when you have these kind of scenarios. So it indicates that several other parameters from the full polarimetric theory needs to be analyzed. That's what we are currently doing. So realistic scattering model. So these three conditions, which I have noted here, are the gray areas now. That is, if the regolith includes ice inclusions, or if the ice is buried beneath the regolith, or if the ice includes a significant volume fraction of rocks. These are very different to model. This, I think I have covered analysis of these CPR less than 1 regions, along with other complementary observations, such as the thermal infrared and neutron data. And we need more polar bistatic observations. For example, if DSR can transmit from the orbit and can be received at ground stations, and we can compare the CPR as a function of bistatic angle, this could provide some new important clues. These are the DFSR polar maps we have been slowly building since 3 years. I will stop here. Thank you.
Sriram, so we have some time for questions.
Thank you very much for the talk. So if you go back to the 2 models that you proposed, will they result in different distribution of ice or different signal if we start to look at other observations, such as the one in the previous presentation? Or do you have like consistent scenario for both observations?
You mean these 2?
Yes. I think we have these 2 models. Is there any other observation that helps us to distinguish the 2, or?
Yeah. So these 2 are the most favorable scenarios in order to get a detection from radar, because if you take this one, so the important condition is the ice should be several wavelengths thick, because if the CBOE has to happen, it has to go through a series of multiple reflections through these icy matrix, and then you will get the intensity double, and then the CPR parameter goes up. Okay, but if it is present in the form of icy patches, then the CBOE is not possible. So the CPRs will be less than 1, and we need to do some other kind of measurements to confirm whether we are observing icy patches or it's just the rocks. So there is a difference between these 2. This will give a definite positive indication. This is tough to determine.
I think the question is, what kind of observations can distinguish between these 2 possibilities?
Okay, so the left one is direct CPR, whereas the right one is you need to observe the total intensity, the components of the CPR. So I mentioned that CPR is a ratio of SC and OC.
No, I think these are really non-radar observations, right? So
Both?
use anything other than radar to distinguish.
Yeah. Yes. Yes.
Okay, let me ask my question. So it appears that the best scenario is when you have a transmitter and receiver both in orbit but not co-located. Would it be a good thing to have like a Gaussian kind of mission with a pair of them following each other and tracking?
Yeah, that's the initial plan for Chandrayaan-1 Minisar and LRO. But unfortunately, before that launch, this was lost.
Okay.
That was the original plan. So you have two orbiters,
Yeah.
and then you transmit from one and then receive from one.
Because I think even if you had a ground station, and if you had a transmitter hitting the polar regions,
Yeah,
the scattering towards the ground station will be extremely small.
extremely small, and you need to get that favorable geometry.
Yeah, so it's only a very few locations that you can
It
scan.
requires extreme planning that you need to slew the orbiter there and then wait for that favorable inclination so that ground will be aligned towards that direction.
Yeah.
I mean, we have been talking with Green Bank, but need to see.
I mean,
if it's feasible or
a
not.
pair of satellites following each other can do a lot more work.
Yes.
They can map the moon with an extreme precision.
Sendil?
Hi, Sriram, I just had a kind of a curiosity question. Are there any mechanism to look at active testing? For example, most of this ice is located in craters, and that's the point. Is it possible to actively heat them, probably a laser in orbit from remotely, and see if the ratios of the polarization is changing and confirm for yourself that this is truly ice? Is there anything in the plans in the long term of such kind of active measurements?
I don't see the need for it. But anyway, we need to be certain that what we are actually seeing is ice, but not the rocks.
Yeah.
This is the first thing to do.
Yeah.
If
So,
we have-
yeah, so if it is locked inside craters and you can evaporate away the ice by some mechanism, and if while you're evaporating the ice, your ratios of left circularly and right circularly polarized light will be changing, and that will give you a confirmatory measurement or probably a calibratory measurement.
Yeah, I mean, that is definitely possible because when this phase changes, I mean, the water is transforming from ice to a liquid,
Yep.
the response will not be the same. There will be a
Yep.
huge difference.
Yeah, so that will be kind of a confirmatory test for your measurements of ellipsometry with radar, that this is truly ice that is being detected.
Yeah, probably that's a good lab experiment to start with.
Sure. No, you can also have a coordinated laser in space orbiting your moon so that you can heat up this crater in a remote fashion while you're doing active ellipsometry with radar.
Yes.
That's a suggestion. Yes, thank you.
Okay, thank you, Sriram.